before, since I see some names here in the list that at least I haven't met before, I thought I can start with a very quick introduction of myself. So I'm an assistant professor here at KTH. I'm very much related to KTH. I did my PhD here, and then I joined our friends in the west coast of Sweden for 3 years, and then came back here as assistant professor since 2018. So in terms of research, so today I'll be focusing on IoT and Web of Things, but in general, what me and my group are focusing on is language-based security. So in a nutshell, is sort of applying techniques from formal methods and programming languages to secure applications. And some sort of prime applications in these settings that we look into are sort of web application, mobile applications, IoT apps, which is the focus of today's talk. And more in general, I'm interested also in low-level security, so very much at the level of architecture and microarchitectures, and also sort of foundations of computer security in general. So these are things that I can talk about in a sense. So if there is interest and you want to reach me out afterwards, then I'll be happy to discuss this further with you guys. Okay, so in a nutshell, you know, the focus here is malicious and buggy code, and that's sort of a real threat in general. So these two are sort of pretty old examples, but it's enough to sort of open up any web page, and you'll see that, you know, security and privacy issues are a real threat in general. So one example a few years back was an Android app which was supposed to sort of implement a flashlight application. Okay, so the only functionality of this app should have been sort of just turning on and off the light basically in your phone. Well, it turned out that it was doing pretty much a little bit more than that. So it was tracking the GPS location of the users and then exfiltrating that to third-party servers, for instance. So the question here is, well, we sort of download these apps and run them on our phones sort of pretty blindly in a sense. So we trust the app platforms that they're doing some vetting, but as these examples show, well, this is a tricky problem, and there actually exist these malicious apps that are doing much more than they're supposed to do. Another example I'd like to point out here is another app which was used in the US. So they have these CVS pharmacies or drugstores that they use basically for distributing various types of medicines. So this app, it was an interesting one because the idea was to sort of use this app to find out the nearby pharmacies in, say, close to your location. So that's an interesting case because the app sort of needs access to your location in order to find out what are the nearby pharmacies. But well, it turned out that it was doing much more than that. So it was sending the location to more than 40 plus other websites. And this is bad in general. So if I abstract away a little bit, so the focus that my research is sort of pretty much about is guaranteeing what is called the end-to-end security. So you have some piece of code, some software that basically is tampering with various types of data that you might have. Maybe the phone and the apps could be a prime example here. So you have some inputs which are sensitive, like location information, for instance, and you have some other inputs which are public you don't care about if they're leaked in a sense. And they're being sort of used by the apps like the flashlight application or the CDS app that I showed you before. And we want to use them to do some useful computation, for instance, showing the list of nearby pharmacies, for instance. So this is a private output that only you as a user of the app should be able to see, okay? But the setting could be that these apps, for instance, could communicate with the public, with some, you know, third-party server, which you might not trust. At least you don't want to learn your location information in a sense. So the goal here is how do we make sure that the apps sort of still use our sensitive data without leaking it to third parties, okay? So now there are various approaches here. So one is called access control. So basically before, you know, allowing the app to access your location, well, in the case of the flashlight app, you can just stop it immediately. You can say, you know, you're just a flashlight app. Why should you need access to your location, right? And there pretty much this problem is solved because basically you just stop it. So you control the access to the information. Well, the problem is a bit trickier when it comes to the CVS application, because the application itself, needs to have access to your location in order to determine the list of nearby pharmacies, for instance. So here you are in a setting where the app should make use of your location, but then the question becomes, how do we track this usage of the location information in such a way that something like this doesn't happen? So if the apps, as it was happening in the example I showed you, sort of tries to exfiltrate it through this, what I call public outputs here, so to some third-party server, then you should stop it, okay? And this is a much trickier problem because now we are sort of in the domain of tracking how this information is being used by the application itself, and then ensuring that it's not leaked out. So there is, a huge research area tackling these problems, and this is what language-based security is pretty much about, sort of combining techniques from programming languages and formal methods to sort of vet these applications, in a sense, making sure that they respect these policies and something like this doesn't happen. So this is, sort of an overview, and you can do this sort of either statically by analyzing the app, or dynamically while the app is executing. You can do some sort of tracking of, say, the location information, and then if it is the case that, this output is sort of affected by the location, then you can just stop it dynamically. And there are various other approaches to ensure this. So that's the general problem, and if you think about it, it has various applications, say, to domains of web security. What I'll show you today, it has applications to the IoT security as well. Okay, but so Internet of Things, so we all know about it, right? So very exciting. Now we can connect various types of devices, right, to the internet. So connectivity, in a sense, is great, right? But something that sort of IoT has been criticized for is that, people start coming up with different standards, different platforms, different technologies. And in a sense, this is sort of holding back the market potential because, it becomes more sort of complex to interface basically devices using different technologies, for instance. And sort of it's a stopper also for realizing, the full potential of the value of the data, because it becomes harder to integrate them all together. Okay, so so IoT, incompatible standard platforms and technology. So can we do something about this? Well, that's where a notion of Web of Things comes into play here. So what Web of Things does is, while IoT sort of provides this connectivity, then Web of Things provides a robust application support for having these devices communicate to each other. And the way this is done is pretty much simple. So you have some IoT devices and you make them available to the web, right? So by making them available to the web, now suddenly you have a unique platform, right, that you can use for having these devices communicating with each other. So I'll show you various examples of that, but maybe one could be, suppose I have a smart thermostat at home, and then I have my phone with me, and I want to have them communicate with each other, for instance, realizing functionality like, if I leave my work location at KTH, then turn on the thermostat at home automatically. So this kind of interactions can be realized using this notion of Web of Things. So this is all great, but then for those of you who have been exposed to the web and web security, well, the web is not particularly known when it comes to security, because sort of every day we see a lot of security breaches when it comes to web technologies. So one of the goals of this work is sort of see, what are the impacts of the security impacts and implications when exposing IoT devices to the web. So how is this realized, this communication between different devices? Well, here there is a notion of IoT app. So an IoT app is just a piece of software that is being executed basically to realize this communication between different devices. I showed you I mentioned the example of the thermostat earlier. So basically, what an IoT app would do is it will sort of check my location, and then as soon as it realizes that I've left KDH, for instance, it will send a message to my thermostat at home, and then it will set it to a particular value. All right. So this is all good. So it sort of connects to this idea of connecting these otherwise unconnected services, basically. And in order to realize that, there are various platforms. So these are cloud platforms called IoT app platforms. And the whole goal is to sort of manage this users' digital lives. So you have things like cyber physical systems, from smart homes to cars, fitness armbands. You have online services like Google, Dropbox, and they even connect things like social networks, for instance. And sort of a particular feature in this setting is this idea of end user programming. So everybody, even without say a computer science bachelor, should be able to be using these apps to realize these functionalities. So what is interesting here is that anybody can create and publish apps. So it's very much like the model of mobile apps. And what we see is that most of these apps are implemented by third parties in this case. So the way they're shipped to the users is either through some web interface, or you have some smartphone client, basically, where you can activate them in your phone. So there are several of these apps. Probably the most known and maybe the focus of today's talk is IFT. So this stands for if this and that. But there are others. So Microsoft has one, Amazon has one, and Zapier is another one. Okay. So IFT is probably the biggest, and they realize this idea of trigger action programming. So if an event happens, then some action is sent to another service. So if I leave my location, then an action is sent to my thermostat at home to sort of set it to turn it on and set it to a certain temperature. So these are quite large platforms. So they integrate, like in case of IFT, 500 services and devices, and they have sort of millions of users, in a sense, realizing this idea of end user platform. So let me give you a few more details of how they work. So the pattern is very simple and very intuitive. So IF stands for if this and that. So if some trigger is activated, then some action should be performed. So on the right-hand side here, you could see an example of this app, which is sort of implementing the functionality of backing up, a photo that you take with your phone to Google Drive. So that's a nice functionality if you'd like to store your photos basically to Google Drive. And what you could see here is, well, there is a name of the app, there is some description. There is some user who created the app. So in this case, it's this guy, Alexander, so some third-party users, and a number of users that are using it. So in this case, you have 94,000 users sort of who have installed this app on their client, and they're using it to realize this functionality. So again, the setting here is these apps have access to sensitive information, like in this case, the photos, right, and the Google Drive account. And then the way they communicate with each other is by executing some JavaScript code in some cloud-based platform, these IoT platforms that I mentioned before. And the question we're asking here is, well, what can go wrong, right? So, sort of given the access to sensitive resources like pictures in this case, then what's happening here is that, yeah, you take a picture, then that's being stored basically in Google Drive. So in order to realize this interaction, right, there is this JavaScript code sort of running in the cloud. So this poses, different threats, because the attacker itself could write this code in such a way that the photo is also exfiltrated to the attacker, in addition to being stored to Google Drive in this case. Okay, so yeah, so if this was a physical presentation, that I would ask you, what could go wrong in this case, but since it's not, then probably I'll postpone this question later and answer it myself. So another example, a useful app would be to automatically get an email, each time you park your BMW car. Okay, and this can be useful because, so you don't forget, where you park your car. And the setting is exactly the same as before. So now you have the app has access to BMW sort of provider, which will sort of track the location of the car, will execute some JavaScript in the cloud, and then will send the map, with the location to, say, Gmail in this example. And again, as we can see here, several users can use this app. So the question we're asking again is what could go wrong here? Okay, so the sort of obvious thing or the first thing one might think of is this app is basically executing some code, in this case in JavaScript. So since that code is can be written by any user, it can sort of exfiltrate it directly, right? So in this case, it could take the location of the BMW and sort of exfiltrate it to an attacker-controlled server. Okay. Well, it's not that easy because one of the promises of these IoT platforms is that they have strong access control. Okay, so what they do basically, once you install this app, then as a user, you explicitly grant access to the app on your services or devices. So in this case, what you do is you trust the platform with accessing your iOS photos in this case, and also with accessing your Google Drive. Okay. So in addition to that, the JavaScript code that is being executed in the cloud is sort of sandbox. So what does this mean? Well, it means that the code is not allowed to communicate, to perform any input or output interactions, basically. So if you merely want to just read the location, the photo here, and sort of exfiltrate it to the attacker, well, it's not possible because they're sort of protecting it in this sandbox. So this is very much similar to the case I showed you before, where the only APIs, this code is allowed to access are the API corresponding to the photo itself and the API corresponding to the interaction with Google Drive. Okay, so that's unfortunate for the attacker. So he cannot immediately exfiltrate this information. But let's see a bit closer how this interaction is actually realized, in the cloud here. So just to remind you, our example again is if there is a new photo, then we want to store it to Google Drive here. Okay, so this idea of connecting otherwise unconnected services. So let's see a bit of the workflow of this app. How is it executed? So the first thing that happens when you take a new picture is that this picture gets uploaded as a new image to Iot, which is the platform itself. And this is fine because you trust the platform, right? So that's sort of one of the premises here. So once the photo is uploaded to the cloud or to the platform itself, then what the platform does, they put this image on a public URL. But what public means here is sort of the URL is public in the sense that if you know it, then you can access it directly, but they contain a long list of random nonces in a sense, which makes it impossible to just guess the URL, okay? But this is just a simple way to realize the functionality, in this case, to sort of send it to Google Drive. So once you get this sort of public large URL, then the only thing that the platform does, it passes the URL to the Google Drive API, and then Google Drive will just use it to upload the photo basically to Google Drive. Okay, so that's the setting here. And now, if we are the attacker here and want to exfiltrate code, say through this JavaScript that we wrote, well, we're a little bit in a bad position because we cannot write code that sort of exfiltrates the photo directly because the code itself is sort of sandboxed. Okay, so private information available through the APIs. I mentioned location and photos here, but can be anything. Can be both voice commands, say from Google Assistant to images and so on. So maybe one way you could think of exfiltrating this information is that if the target platform is sort of some public services like posting it on Facebook and so on, then you can directly, take the picture, post it on Facebook so everybody can see it. So you could do that attack, but that wouldn't be very stealthy because then the user itself, will see that, well, something is wrong with this app, and then they will start using it, will stop using it basically. So yeah, you could look at these public things in a sense, but that's not very stealthy. So in a sense, what you could do here is you can sort of load the gun by accessing these APIs to JavaScript code, but you cannot pull the trigger basically because the code is sandboxed. In order to implement the attack in this case, and that's what we found in this work, is that we can use exactly this system that the platform is using for communicating with different services in order to exploit it. So if you remember the case I showed before, so what it will do will create a random public URL with the image, and then at some point it will pass it to Google Drive. Okay, so these are the only APIs that you are allowed to use, say, as an attacker. And the trick here is that you can still use these APIs, which you're allowed to, let's say, sending information to Google Drive, but you can do this in a malicious manner. So there are two ways that it is possible to exploit this. So the first one is you take this public, unguessable photo URL, which you can access, since you wrote the JavaScript code, and then instead of sending it to Google Drive, in a sense, to the respective API, what you do is that you send it to your own server. Okay. And then as a parameter of that, then you encode, the actual URL. So I'll get into the details of this in a bit, but what's happening here is that instead of communicating directly with Google Drive, you'll just send this to the attacker, and then you can configure the attacker server in such a way that now the URL is sort of forwarded to Google Drive. So from the user's perspective, the attack is completely stealthy. They won't even realize that something wrong happened because the photo will be properly stored into the Google Drive. So that's one way of doing it. The other way is using what we call the URL markup attack. So in this case, instead of sort of using the APIs for communicating with Google Drive, you can in some cases use an invisible image. Okay, so what this means is that as part of your, say, sending an email, for instance, you can include an image which is sort of 0 × 0 pixels. So when this is rendered in by the email client, this will be completely invisible to the user. But what actually happening here is that the secret information, like this photo URL, is being passed to the attacker. Okay. So I will dare to make a live demo here. It worked earlier, so I really hope that it will work again right now, but just to give you a feeling of how these systems work. So here is a view of the platform. So the app we're going to implement, since I have an Android phone, I'll use an Android photo service. So basically the app will trigger each time I take a photo with my Android phone. And then the functionality I want to realize here is to save this photo, in this case in Dropbox. Okay, so the idea of the app is similar, but services that I'm using here are Dropbox and Android photos, basically. So what happens here is when I'll take a picture with my Android phone, and I'll do it in a second. Then the app itself will provide me some API for reading, the URL of this photo. Okay, so what I'm going to do with that is instead of sending the URL directly to Dropbox, I'm going to send it to my own server here and then encode it as a parameter, basically, to the request. All right. So let's see how this happens. So I can already show you my own server here. I can refresh it. You can see that there are 5 photos here. And then this is my Dropbox account, which has three photos stored in it. Okay. Oh, actually, so there is nothing now in the server since the log sort of got updated. Okay. So here is my Dropbox, and let me see if I can take a picture. So I'll take a picture from my window here, so you guys know that I'm not sitting. Okay. So now what should happen is that since I took a picture, then the app I showed you before here should trigger. So I have installed it on my Iot client, and it should save this photo on Dropbox. So let's see if this works. Otherwise, we might have to wait a bit. Okay. Take another picture. See if I have, yes. All right, excellent. So if you see my Dropbox account, so what happened is that I took a picture from of KTH from my window. So it was properly stored in my Dropbox account in this case. So now if we look at the server, the attacker server in this case, and then I refresh it, then what's happening here is that you hopefully see the same picture. Okay. So in this attack, what happened is that instead of forwarding the URL of the photo directly to the attacker, then this goes first to my server. The server stores it, and then it sort of forwards it to Dropbox. So from the user perspective, everything is sort of stealthy and nice. Okay, so this is a case of this URL upload attack, and this was for Iot. So another example with the markup attack is in the case of Microsoft Flow platform, which is an alternative platform used by Microsoft Flow. So I have a video in this case. So what happening here is that I want to realize the following functionality. So if I post something on my Facebook wall, then send me an email, with the picture or the photo that I just posted. So you can play the same game here by using this 0 times 0 image. So I sort of test the app here. So I'm deploying it on my own interface as a user. Then I go to the web, to my Facebook, right up, upload a picture. So it's a pig in this case. If you like pigs, right? Some people do. Then you just post it, and now I should receive an email, right, with the photo that I just posted. Okay, and indeed, if in this case, if we go to the Gmail, then we can see that basically the photo was correctly forwarded to the user. But then what happens is that in addition to that, the photo was also forwarded to the attacker. So this is pretty bad, given that most of these apps are implemented by third parties, and they are they're used by millions of users in general. Okay. When we look at this attack surface here, I focus mainly on privacy in a sense, so exfiltrating things like location or photos or email subjects and so on. But the problem becomes sort of even trickier when it comes to integrity and availability. So you could write these apps in such a way that, say, when I send a command to my thermostat at home, instead of setting it to, I don't know, 30 degrees, it would set it to -5, for instance. So of course, integrity attacks are possible, but they cannot be as stealthy as confidentiality or privacy attacks I saw before, because the user ultimately can see the effect on their own devices, but they're definitely possible. So what we did is, given these attacks that I showed you before, is we said, okay, let's see how they appear in the wild. So we went to this platform called Iot and sort of collected about 280,000 apps, did sort of a classification of what services were sensitive and what were not, and tried to sort of estimate, what is the potential risk, right, when it comes to both privacy violation, integrity violation, and you could see things like availability violations as well, because you could have the app simply stopping, to perform an action. So that can be realized. And what we found was, pretty shocking in a sense, because 30% of these apps could potentially be vulnerable for privacy attacks. So that's pretty bad. So before I move to another simple attack, I'd like to stop for a second and wait if there are any questions from the audience so far. Any questions? Okay, good. So yeah, so there were these two different ways, right, of exfiltrating information, but turns out that there is an even simpler one, which is it's really serious here. So maybe some of you know about URL shortening techniques. So what I mentioned is that when you upload a photo or something triggers, then this is being uploaded to the cloud, and then the cloud will create this long, URL that is public but is unguessable in a sense. So now it turns out that these services allow for URL shortening. So instead of sending via email this sort of huge long URL, they use one of the URL shortening service in order to basically calculate a short URL, which there could be different reasons for wanting to have URL shortening. So there is a list here, so what happens in this case is that these have some shortcomings which are really known, right? Because now you're sort of lowering the entropy, right, of this public URL in a sense. And maybe you've heard about the brute force attacks, right, on Zoom, for instance, where people started sort of randomly guessing channel IDs, right, and then joining channels that were open to everybody. So having this low entropy of shortened URLs is really serious in this case, because now you can start, just trying out different short URLs, and then you can get basically sensitive information by users from users uploaded to the platform itself. So the attack is pretty simple here. So what happens in IFT is that when the shortening is enabled, then all these unguessable long URLs, they're replaced by short URLs, containing 7-character long strings, basically. Okay, so the whole URL is sort of casted down to this short URL where the random part is sort of 7-character longs, and the first character is always fixed, is a 7 basically. So it's sort of the entropy is 6 characters here. So, since we have the 6-character string, what we can do is basically just randomly try out different. And then what we realized here is that we had the 2.5 success rate on a test of 1,000 requests. So for every 1,000 requests that you try to guess these URLs, well, you have a success rate of 2.5%, which is huge. And something that sort of was shocking here is that at the time where we discovered this, then the URLs were being served over HTTP, so which opens them up to integrity attacks, basically by a network attacker. So that was pretty bad. And then how do you fix this? When I'll get back to that in a second. But so this is the state of the affairs, right? So the malicious app maker has the possibility, basically, of affecting these services and collecting sensitive information by the user. So what do we do about this? Well, if you talk to these guys, right, and then you propose something more principled or researchy, of course, it won't fly immediately, because it will sort of change the way that they're working and the way they're vetting these apps and so on. So First countermeasure that we propose here is something as simple as a per app access control. So what does this mean? Well, it's sort of breaking this flow that is causing the information leak here. So if you have an app that it doesn't access any private sources, then you say this is fine. You know, it can implement any sensitive code there. Well, there are no sensitive sources, so we're done. Then you can classify an app as private, so it doesn't have any public sayings in this case. So what you could do is, well, tackle the problem by actually providing some sanitization, you know, at the point where we were exfiltrating the information before, okay? So you could do things like, well, you cannot combine, you know, this, you cannot build URLs from strings, but only use APIs. So of course, this would limit the functionality of the app, but it will sort of make it secure. Or you can just sanitize the output in a standard way. And then when it comes to URL shortening, well, there, you know, you just have to make them longer. And best practice in this case is using 11 to 12 characters. Okay. So for instance, regarding this classification, right? So you can consider an app public if it's realizing a functionality like the following. So there are apps out there implementing that, you know, if an astronaut, for instance, enters the space, right, then you get a notification. So maybe this is not a sensitive source in a sense. So you can just allow the third-party user to implement any code there, because even if he gets to know when the astronaut entered space, well, this is not sensitive in this case. And then what can you do with private apps, like the case of location and BMW? Well, here you can just disallow the attacker, the user completely to implement filter code, basically. So you can just connect them directly yourself as a platform provider. So of course, this limits the functionality, but it sort of brings security. So this is sort of a short-term countermeasure in a sense, but in the long term, the core of the problem here is, of course, you want the apps to have access to your sensitive data. I mean, that's the whole point of using them, but you want to track the flow basically and ensure that whenever, you know, you're sort of sending this information to the attacker, then you'd like to stop those, and, either statically by analyzing this app or dynamically, basically. Right, so that's what we propose as a long-term sort of countermeasure. And what is good in this setting is that since these are emerging domains, right? So they and this code that is being executed is pretty simple. So we're talking about maybe up to 100 lines of code, so not more than that. When it comes to techniques like information flow, tracking the information throughout the app, then there is huge potential there for making it applicable to this scenario. And indeed, what we do here is we sort of implement a dynamic information flow tracker called JS Flow, which basically will track, you know, once the app uses the location information, it will track how it is used inside the code dynamically. And then if it happens that, you know, it's being sent to something that you don't trust, like the attacker, then it will stop the execution while you're running the app. I have a bunch of examples here showing what I already showed you before, but maybe yeah, given the time, maybe I'll skip those. But this is sort of the example of the attack that I mentioned before. Okay, and there are various ways you can leak information using having, you know, the power of writing the code yourself as an attacker. So you can do it explicitly or implicitly through programming languages convert. So it's a tricky question in general, but maybe for this setting, you know, we understand the techniques for solving this pretty well. So the hope is that, yeah, at least in this setting, these techniques could fly. Okay, so let me show you what we have as a vision here is that instead of, you know, trusting this third-party code blindly, to be executed by the platform, we want to sort of extend this with what we call information flow control. So what this means is exactly this sort of tracking of information through the execution of the program. And then if something fishy is happening here, there, and the app is exfiltrating information, then you can just stop the execution. Okay, so there are some formalization, of course, that what we're doing is sort of sound and secure. So of course, we sort of coordinated the disclosure of this with the platform providers in this case. The story is quite interesting here. So I won't name names here, but while one of the providers sort of recognized the issue, the other said, okay, that's fine. We can just put a note on our web page saying that if you do something bad, then we'll kick you out of the platform. So not very useful, but yeah. And then the other provider said, yeah, this is an issue, but we don't care. So you can see the attitude to security in general, unfortunately. Okay, so here is a demo about the monitor, but I will sort of skip. What I would like to conclude with is that one might say here, well, yeah, they're not doing the vetting of this app, but if they did that, then they will capture, this kind of attacks that you're proposing. Well, it turns out that the story is much worse than what I told you about. Unfortunately, this is work in progress, and we're coordinating the disclosure, so I cannot tell you much about it. But what I can tell you now is that, a single malicious app of a single user, say me, suppose that I'm the attacker here, is able to attack any app of any user to exfiltrate this sensitive data. Okay, so in this case, I don't even need the app the malicious app to be installed by, say, some users I want to attack. I can just install it myself, and then the way they're executing these apps in the cloud allows me to basically get any information of any user handled by this platform. Yeah, so maybe I can come back in 6 months or so I can tell you more about this if you're interested. But just to conclude, so this is one aspect of the work on the IoT platform that we're doing. So there are some ongoing works, very exciting here. So one is proposing an IoT platform now that tackles these challenges. So instead of blindly trusting the code, we sort of make this platform security aware. And the second project is sort of related to what I couldn't tell you about, but the reason here is that while these apps are executing in some sandbox, it turns out that these sandboxes are not good enough in a sense. So you can escape the sandbox and then attack different apps of different users by collecting all this sensitive information. So we're doing some work on improving that. And the final sort of project, and this is related to one of the digital future projects that we're involved in, it sort of relates this notion of trusted execution platform. So while the setting I showed you today, the user can trust the cloud with all their sensitive information, right, and hopes that the cloud will not exfiltrate it in any way. Well, it turns out that there have been some developments of sort of hardware modules that allow to privately execute sensitive apps, like the cases we saw today, in an untrusted cloud. So if we are able to sort of leverage these trusted execution environments, as they're called, then we could have users still, make use of the functionality of the cloud, but they don't have to trust the cloud because, that functionality is sort of protected by this trusted execution environment. So if any of these topics sort of rings a bell to anybody, I'll be happy to discuss this offline. Okay, so this is a summary of things I told you about, but I'll just leave it there just to sort of inspire some questions. Otherwise, thanks very much. And yeah, I'll be happy to take some questions now.